Well, hello once again. To get started, there may be a few late struggles, but I'd like to get things started. The session we had this morning took around 45 minutes. So once again, I appreciate taking the time to join our webinar today on local grid refinement in Visual MODFLOW Flex. My name is Wayne Hesh. I'm the product manager for Visual MODFLOW Flex here at Schlumberger Water Services. So what we'll go through today is a review of the traditional approaches to grid refinement and the pros and cons of each, which are probably pretty familiar to most of you that have worked with groundwater modeling over a number of years. Then we'll take a look at local grid refinement and discuss the theory behind it, some of the pros and cons and the benefits. We'll take a look at how that's implemented in VMod Flex. I have a few short slides on some of the future developments, what the USGS is currently working on. And then we'll do a live demonstration within the VMod Flex environment, and I'll provide you a few links where you can find some more information on how to download the trial version or register for future webinars and training, etc. So I've shared everyone's microphone I've muted all the microphones just to prevent any feedback. If you have any questions throughout the session, just use the chat feature that's available in WebEx, and I'll do my best to answer the questions for you. If not, we'll open up the microphones at the end of my talk, and we can have a discussion at that time. So first, some of the approaches to grid refinement. The first is using globally refined grid. The pros to this would be the easeability at which you can build the grid. I mean, a few mouse clicks, and you've got a grid that's 200 by 200 or 500 by 500. It can yield reliable results. There's no limitations for when you want to do contaminant or particle tracking simulations. The drawback, however, that it creates a needless amount of grid cells outside the area of interest, and this can result in longer simulation times. The variably spaced grid is probably the one that's most often used. You have the benefits of this is a regular structure between adjacent cells. You have just a single set of Modflow files, so a single model. And this is what's most commonly used if you're doing contaminant transport or particle tracking, so you refine the grid around the area of interest. The drawbacks, obviously, is that it creates excessive cells outside that area of interest, so the rows and columns extend all the way to the edge of the model domain. This can result in longer simulation times. It's not ideal if you need to do multiple areas of refinement, so for example, multiple well fields at different spots in the model domain. Essentially, you'll just end up with a globally refined grid anyhow. It can result also in cells with large aspect ratios or adjacent cells, so for example, tall and skinny cells beside uniform cells or short and fast cells, and this can result in instabilities and numerical errors. It's a little bit more work to build. Obviously, the GUIs that are available make this pretty easy in design. The other drawback is that you can't have any vertical refinement in the local area of interest. The other approach is telescopic mesh refinement, or TMR. It's rather straightforward, flexible, and easy to use. Works well for some cases, but not all problems, and it's generally computationally efficient. Drawbacks are that it's only one-way coupling from the coarse grid to the local grid, and there's no feedback from the local grid to the coarse grid during the course of the simulation. So this means that the onus is on the modeler to check to see that after running both models, that the heads and the fluxes across the interface from those boundaries is consistent. If they don't match, there's really no formal mechanism for adjusting the models to achieve better agreement. The other drawback with TMR is that you can't have any vertical refinement in the area of interest, and there's no support for contaminant transport or particle tracking across the refined model and the coarse or global model. So having said that, in around, I believe, 2005, the USGS released the Modflow LGR package, or local grid refinement package, and the next couple slides decide the theory and how it works. So with Modflow LGR, you have a two-way iterative coupling of one or more Modflow 2005 models. So this means that the heads and the fluxes are balanced across the shared interface boundary between the parent grid and each of the child grids. The shared node approach, which means the grids are constructed so that the nodes of the parent grid are coincident with the selected boundary nodes of the child grid, and the next couple slides will show what that means. You start with your parent grid. You define a refinement ratio for the by which your parent grid should be refined for corresponding child grid cells. And this is an odd integer between the range of 3 to 1 all the way up to 99 to 1. Each parent cell is then split into the corresponding number of grid cells, and by using an odd integer, this results in a cell in the middle that has a consistent location between the parent and the child grid. The area of the parent grid that is covered by the child grid is set as inactive cells during the course of the simulation. A few drawbacks are that the child grids cannot overlap, and also the child grids must have the same angle of orientation as the parent grid. During the translation, this produces a set of Modflow files for the parent grid and an additional set of Modflow files for each of the child grids. The Modflow LGR engine is launched using a control file with the extension .lgr, and this is the alternative as to what is typically done using the name file. A short illustration to reaffirm how that works. You start with your parent grid design. This doesn't necessarily have to be a uniform grid. It can be a variably spaced grid as well, and it can be rotated or shifted to world coordinates. You then specify your child grid region with the appropriate refinement ratio. And then, as I mentioned, during the course of the simulation, the cells that are overlapped by the child grid and the parent grid are set to inactive. The green square or rectangle that you see on the screen, that's what we refer to as the parent and child grid interface, where you have some shared nodes between the parent and the child grid. This is also where the flow and head boundaries are calculated if you want to take either the child or parent grid model and run those independently. That's where the head package is created for that. So following up, as I mentioned, LGR run produces a .bfh, which is a new package for Modflow LGR called boundary flow and head. And essentially, it's a time-varying flux and head boundary condition at the interface between the parent and the child grid. This allows you to run either model independently using this as an input for the boundary conditions. And this is ideal if you want to do particle tracking or contaminant transport. Some of the pros of Modflow LGR are quite obvious. It creates cells only in the area of interest, so you no longer have those rows or columns that extend all the way out to the edge of the model domain. And this generally means that it's less computationally intensive. You can have up to 9 child grids within a single parent grid. So if you have several well fields, you can create more than just one child grid if you wish. Again, with the consideration that they cannot overlap. And just a comment, each child grid can have a different refinement ratio. You don't need to have the same refinement ratio applied to each one. You can have vertical refinement in the child grid region that is different from the parent grid, and there's a short illustration that shows that in the next few slides. The key benefit, though, is that there's two-way feedback between the coarse and the local grids, and this ensures that the models have consistent boundary conditions along their joining interface. And this is probably one of the significant benefits of LGR over telescopic mesh refinement. The grids are generally easy to design, and certainly the graphical environment of VModFlex really facilitates that, and also the Modflow LGR results can offer immediate results. Some of the drawbacks or disadvantages of Modflow LGR is that there's no support for contaminant transport across the parent-child grid interface, and that was last time I checked. I'm not aware of any updates to MT3DMS or the other transport codes that support that. Up until last year, there was no support for particle tracking across the local and child grid interface, but that was addressed in an update to ModPath, which was released last year. So that's something that we'll work on in the near future. As mentioned in the previous slide, you can have up to 9 child grids, so I kind of consider that a pro and a con. So it's really designed if you want to have just a few areas of refinement, but it's not, Modflow LGR certainly isn't designed if you want to do refinement around all your wells or all your flow boundaries, for example. The other drawback is that once you start dealing with more than one set of Modflow files, you can have a number of different inputs, translated Modflow packages and results that you need to manage. So file management can certainly become an issue. So a short illustration of what that looks like. You've seen this picture in the previous slide. You have the red grid represents the child grid that you assigned on top of the parent grid with the 3-to-1 refinement ratio. And you'll see that area is blown up in the illustration on the right. You'll see each parent grid cell is then split up into 3 child grid cells. and the green circles represent the shared nodes where you have a child grid cell center overlaying a parent grid cell center. Another illustration that shows what the child grid looks like if you use 11 to 1 child grid refinement. So essentially, you can go down from 300-foot grid cell dimensions in your regional model or your parent grid, right down to 27 feet or approximately 30-foot child grid cells. You don't need to have a transitional area where you go from gradual cell size changing. Now, that's not to say that having a higher refinement ratio in the child grid can lead to more accurate results. I believe there's some comments in the Modflow LGR documentation that suggests that using a higher refinement ratio doesn't necessarily yield better results. So I encourage you to take a look at that package document at your own leisure. I mentioned one of the other benefits of Modflow LGR is that you can refine the grid vertically in the child grid region. So here's an example of a cross-section along the parent grid column 10, and this will be the example that we show in the demonstration shortly. You'll see you have two layers in the parent grid, and these are illustrated with the annotations there. And what we did when we created the child grid is that the layer 2 was refined by a factor of 3 to 1 in that region. And this is ideal if you have steep hydraulic gradients or complex geological structure. It may help in alleviating the stabilities. Another illustration that shows 4 child grids generated on top of one parent grid. Again, these can have different refinement ratios and can have different vertical refinement aspects as well. So I mentioned as the conversion of the Modflow LGR to the Modflow files, it creates parent and child models. So for each of the packages that are used for that model, whether they be the basic package, the discretization, constant heads, rivers, you'll see a Modflow file for the parent and each of the child grids that are generated. And the same is true for the results. So after running Modflow LGR, you'll have an HGS file, a DDN file, an LST file for the parent grid and for each of the child grids. So some of the benefits on how we've provided support for LGR and VMod Flex are as follows. The first is that you have real-time visual aids when you're designing the child grid. So when you're specifying where you want that child grid to start and end, you can add any appropriate data objects, whether or not they be well fields or geological features, etc., to help you position where that grid should be. The conceptual model approach really dramatically facilitates populating the parent and child models, so you don't need to worry about if your shape file that you have should be translated to the child grid or the parent grid. This is done for you automatically once you build the conceptual model in VMod Flex. So you design the geological structure, design your rivers or your well locations with shape files or other GIS data, and then the translation and the cell assignments are done for you automatically. This also allows you to have high resolution properties in your area of interest. So quite often if you're designing regional models, you may have more detailed borehole logs in a specific area of interest, so you have higher resolution connectivity values, initial heads, etc. So with LGR, you can populate that child grid region with maybe a higher density surface or ASCII grid, etc. And then the areas where you're not sure if you have as much data, you can have coarser properties assigned. And again, this is done for you automatically during the conceptual model conversion. The iterative approach in VMod Flex allows you to compare several numerical models, not just a single numerical model. So for example, if you're not comfortable with LGR, you can generate a variably spaced grid from your conceptual model, populate that model, run the model, and take a look at the results. And then you can generate a scenario with local grid refinement, generate a numerical model for that, and also within it, with a few clicks, generate the inputs, translate and run it, and take a look at the heads. So it's pretty much unlimited how many numerical models you want to create from a single conceptual model. In addition, if you're not, if you're learning LGR and you're new to the capabilities, you can also assess various grid refinement scenarios. So for example, you can try a child grid that has a 3-to-1 refinement aspect. With a few clicks, create the inputs, run the simulation, take a look at the heads to see if it's giving you the results that you want. If not, you can go back and generate a new LGR finite difference grid with a different child grid refinement aspect and generate another numerical model. So it's, again, it's an iterative approach that allows you to compare several numerical models for your project-specific needs. And lastly, as I mentioned, you're dealing with several Modflow files, cells, calculated results for both the parent and the child grid, and we offer efficient means for managing the data objects and the files within VModFlex. So these include both the input parameters, whether they be constant head cells or river cells for the parent or the child grids, connectivities for the parent and the child grids. You can easily access and edit these from the model tree. And then when we do the translation to Modflow, these are managed in appropriate folders on your hard drive or whatnot. So that's an overview of Modflow LGR. We'll go into the demonstration shortly. I want to talk a little bit about some of the future directions that the USGS is currently working on. For anyone that's on the line that attended the Modflow 2011 conference last year, you may have been fortunate enough to hear the introduction about Modflow USG, or the unstructured grid version of Modflow. This is a finite volume approach. They're currently working on finalizing and reviewing the Modflow USG code, and we're hoping that something will be available sometime this year. So with Modflow USG, you can have nested grids both horizontally and vertically, which means you can have local nested grids around any number of wells, flow boundaries, whether they be streams, rivers, etc. These nested grids don't need to span all the vertical layers like they do with a finite element approach. This is works with a single set of Modflow files, so you don't have multiple files like you would with Modflow LGR. As I mentioned, it was presented last year at the Modflow conference. It's still in development, and as mentioned, once it becomes available, we'll start working on this within VModFlex. A short illustration that shows what this looks like. For those of you that have worked with fee flow models before, you know that one of the first steps in designing the model is to add the design the super element mesh. In this workflow, you provide the geometrical inputs that you want to use as inputs for the mesh design. So you define your boundary, you provide a set of polylines that represent your flow boundaries, points that represent your observation targets and your well locations, and these are used as inputs for the mesh generation. So you can automatically refine the mesh around these well locations or the flow boundaries. So the approach we'll take with Modflow USG is very similar. You have a set of conceptual objects, so lines that represent your flow boundaries, your well locations, and then when you generate an unstructured grid, you can automatically build nested grids around these objects in VModFlex. There's a question that came in. Does the use of LGR prohibit the use of grid refinement in the parent grid by other means in areas outside of the area that overlaps with the child grid? The answer is no. You can still refine the parent grid in the other regions that aren't covered by the child grid. I hope that answers your question, Steve. Another question that came in, what are the available two-way boundary conditions? I'm not sure what you're asking there, but essentially Modflow LGR supports all the standard flow boundaries like your river, lake, constant head, drain packages. The boundary condition that is generated after the LGR is run is a package, as I mentioned, .bfh, which contains the heads and the fluxes at that interface. I believe the only restrictions, as I mentioned previously with LGR, are the transport package is not supported, and I believe there's some solvers that aren't currently supported. Sorry, to clarify, the question was, what I mean is on the shared nodes, what boundary conditions does the program use? So to answer your question is, during the LGR run, Modflow LGR calculates flow and head boundaries at the interface where the child and the parent could overlap. So essentially, it generates this new flow and head boundary flow and head package, which contains heads and fluxes as the model couples and iterates between the parent and the child grids. Question from Jason, are parent and child automatically added to the file names? The answer is yes, we do that. Any limitations on the number of total cells, including both the parent and the child grid? No, not that I'm aware of. One of the other benefits of VModFlex is that it's a 64-bit application now in addition to 32-bit, so you can build some pretty significant size models if you need to. Just to get into, obviously, slowdowns when you need to populate that grid with the conceptual objects, and then when you do the translation and also runtime. So I haven't really reached any limits yet that I'm aware of. I mean, certainly you can build parent grids that go up into several 100,000 nodes and also child nodes as well. Again, if you have any questions at this point, just feel free to use the chat option. I will go to the next slide. Yeah, here are some of the references that we mentioned that I mentioned in my presentation. And at this point, I'll unmute the microphones in case anyone else has some additional questions they want to ask. Sorry, Bob, I think you had a question, is that right? Just a remark before we go on, I want to thank you for attending. We'll go into the live demo now. As a registered attendee for the session today, you're eligible for a 20% discount on our online training that we're holding for VModFlex. So if you're interested, just email our sales team, sws-sales@slb.com, or visit our website. So I'll proceed on to the live demo now. I'm just going to mute the microphones again. If you have a question, just please use the chat feature, and I'll try and answer your question for you. So what we have is a simple model here where the conceptual model is already built, and this sample project is available if you choose to evaluate the trial version of VModFlex or if you have a license. We have here a simple model with two geological formations, a upper aquitard and a lower aquifer. We have a few pumping wells located in the middle of the model domain. And we have connectivity assigned with a constant value to both the top and the bottom formations. I'll just pause at this point. There's another question that came in. Clarification on the cell size. Are there limitations on the total number of cells, including both the parent and the child grid? No, not that I'm aware of. Any total sum of cell size, the total number of cells, I'm not aware of any limitations. Question from Mehmet: did you test the results through comparison between numerical and analytical solutions? The answer is no, I have not, but if you refer to the Modflow LGR package documentation, I'm sure they've done some benchmarks that compare LGR to globally refined grid and variably spaced grid. Question from Dave: does VModFlex use a modified code for LGR or is it the USGS version? Also, is there a way to easily update the LGR version? We use the standard USGS code. The only thing we've added to it is the support for the SAMG package, which is proprietary. I'm not sure what you mean if there's an easy way to update the LGR version. When there's a new version that comes out, we'll certainly add that to our interface, but there's currently no option if you want to use your customized LGR executable. I mean, in theory, you could take the translated files that are generated and run those outside if you wish. So we have a conceptual model built, which consists of the geological structure, so your layers, or your horizons, I should say. You have your solids here. And we have flow boundaries, so your constant head, your river, and your wells. Once the conceptual model is built, you have the option then to proceed to designing grids for Modflow or design a mesh for TFlow. So we'll go through a simple finite difference grid scenario. We'll start by designing a uniform parent grid with just a coarse cell size. You can see what a cross-section of that grid is going to look like. We'll just use a deformed grid for this example. And the grid now appears in the Flex viewer. To define a child grid, we're going to load the Define Child Grid option. And this is one of the benefits, as I mentioned previously, is that you can provide any of the data objects to the grid input screen to help you position where that child grid should be. So we want to create a child grid around our 4 wells in our well field. And we're going to just position where the start and end location should be. And here's that refinement ratio that I mentioned before. So you can go from 3 to 1 all the way up to a factor of 99 to 1 for your child grid. You click on preview and we'll see a preview of what that child grid looks like. In the second screen is where you specify the vertical child grid refinement options. As I mentioned, you can have the vertical layers refined by any specific factor in that child grid region. And you have option to apply that globally for all layers, or you can have specific layers have different vertical refinements. So the options are to refine the vertical layer by 3 to 1 all the way up to 9 to 1. So we'll leave the default options as they are for now. After the grid is created, it's added to the model tree, and you can see what the parent and child grid look like. And you can also show that in cross-section views along a row or column, and span through different columns and rows, etc. Now that you have your grid generated and all the conceptual model data designed, you can generate a numerical model. So we're going to run the conversion to a numerical model. What it does now is it reads the properties, the geological layers, the attributes you define for your bounding conditions, and the grid geometry, and creates the corresponding numerical model inputs. So what you'll see in the tree in the bottom left here is now you have a numerical grid with corresponding flow properties, bounding conditions, and corresponding inputs for both the parent and the child grid. You also have your wells, etc. Once the numerical model window loads, you have a workflow navigator here, which allows you to proceed through the different steps of the numerical model. That's one of the significant differences in VModFlex, is that the steps for building both the conceptual and numerical model are laid out in an easy-to-use navigational workflow aspect. So first, you can see the properties that appear for the parent grid and for the child grid. You have the database where you can see the values for KX, KY, KZ in the different zones. For the conductivity, we use the constant value for both formations. If you take a look at initial heads, you can see that you have distributed values for the initial heads. You can mouse over and see what the initial head values are. And you'll see, if we turn on now the initial heads for the child grid, that you have a much more higher resolution values in that region of interest. Proceed to looking at the bounding condition cells. You'll see we have the constant head cells. These were generated from the conceptual bounding conditions that we generated, and I'll just show you what those look like again. So in our conceptual model, we had a polyline on the west side of the model domain, another polyline on the east side of the model domain, and we had this polyline that represents your river location. So when the numerical model is generated from the conceptual objects, you'll see you have the corresponding bounding condition cells that resulted. So here's what you see are the river and continent cells for the parent grid, and here you can see now the river cells for the child grid, which have much more binary resolution. The properties and bounding conditions can also be viewed in along cross sections in rows or columns, and they can also be viewed in a 3D view. That's one of the significant benefits of VModFlex. You have this flexible viewer where you can easily switch between cross-sectional views, plan views, 3D views during the course of your model development. At this step, you can design inputs for zone budget zones. If you're doing a Modflow 2000 run or 2005, you could define particles, obviously. We're going to add our calibration targets to this step as well. So we're going to use some observation wells that I imported from a spreadsheet that contain observed heads at different locations in the model domain. And now these will appear in the model tree and also shown in the model domain. So if we span through different layers, you can see different observation points that lie in the child grid and also in the parent grid. And these are represented by the green points on the screen. There's a quick question before I proceed. How does it deal with the river at the intersection of a parent and child grid, say the coarse grid at the parent level and the finer level? Hopefully the illustration I just showed the answer to that. So you can have river cells that exist in the parent grid from the same reach, and river cells that exist in the child grid. And then during the two-way coupling, Modflow LGR automatically calculates the appropriate heads and fluxes between those two numerical models. So at this step, you can choose to run a single run, and in the future run parameter estimations. This is something that we're currently developing in VMod Flex, and we should have an update to that available in the coming months. So we're going to choose to run Modflow LGR. At this stage, you define the translation settings, so the solvers, your packages for output control, anisotropy, etc. LGR has its own specific settings for relaxation factor and head and flux closure criterion. Usually the defaults that are provided are ideal in most cases. I'll just adjust these a little bit to decrease the simulation time. So then we translate the numerical inputs into Modflow LGR files. At this point, I'll show you the files that result from that. You'll see in the working directory you have now a set of files for the child model and for the parent model. So we have all these files here represent the different packages for the child model, including the required packages, basic package, discretization, etc. This will contain the river cells for the child grid region only. And then you also have the files for the parent grid. This LGR file is the control file I mentioned, which serves as the input for the Modflow LGR engine. It basically tells the engine how many how many child grids exist, what the dimensions are, etc. So we'll proceed on to running Modflow LGR. Click the Run button. So you see the convergence criteria, the number of iterations that are required, the closure, etc. After Modflow LGR is run, we can view the results in the forms of maps and charts. And you'll see also after a successful run that you have the heads and drawdown are added to the output folder in the model tree. So you have a set of heads for both the parent and the child grid, and a set of drawdowns for both the parent and the child grid. So what you're viewing now are the parent heads. I mentioned previously that during the course of the LGR simulation, the cells that are covered by the child grid in the parent grid are set to inactive, and you can see that as I mouse over here, and you can see the status bar down below, that those are inactive cells. What we do in VMod Flex for both the heads and the drawdown is we interpolate the values from the child grid onto the parent grid in order to have continuous color rendering for both the contours and the color shading, just for more effective visual representation. So if you wish, you can see just the child grid heads by turning this off and turning the child grid heads on from the model tree. You can mouse over, you can see these along cross sections. In 3D view, you have your color legend here that helps you correlate what the calculated values were. And likewise, you can see the drawdown for both the parent model and for the child model. As I mentioned, this can be viewed in layer 2D views, whether they be plan or cross-section views, or you can also view these in a 3D view. So if you want to see, try that again. So you want to see color maps along specific cross-sections, you can scroll through those rather easily. Here you can also position other data objects. So for example, your wells, if you want to see your river cells, how they intersected with the model, other flow or boundary conditions, for example, these are all accessible through the 3D view. So you essentially have a real-time 3D aspect during the model design and the analysis stage of your project. Lastly, we'll take a look at the charts that are generated. So you can see your calculated versus observed heads for both the parent grid and the child grid. So we'll first take a look at the observations for the parent model. You can see different observations, what the calculated observed value is. And you can filter these by different layers if you wish. And if you select the child grid option, you can see just the observations that lie in your child grid region. In this case, we only have observations in layer 2, and you can see the corresponding observed versus calculated values. If you click on the mass balance charts, you can see the analysis of the LST file, where you can see corresponding inputs and outputs for different packages, fluxes, etc. So this is a single LGR run from your conceptual model. As I mentioned, one of the benefits of VModFlex is that you can now go back and assess a different grid representation, whether it be a uniform grid or a globally refined grid, or we can go back and generate another set of numerical model files. So if I go back to the grid generation step, I can create another LGR run with, for example, a larger parent grid if you wish. You can then add a new child grid onto that region with whatever refinement ratio you want. So we'll specify roughly the same start and end location. And this time we'll use a higher refinement ratio, say 7:1, for example. After you do that, the new numerical grid is added to the model tree. So let me just collapse some of these things so you can see. So from our single conceptual model, we now have the first grid that has the corresponding inputs and results. And then we can take a look at another numerical model with from a different LGR grid design. Since we used a higher refinement ratio, it's going to take a bit longer to calculate the heads, the properties, etc. And you'll notice now that it's loaded another instance of the numerical model workflow where you can proceed through the steps for boundaries, properties, etc. If you arrange the different windows, you can now see what different workflow windows you have available. So we had our conceptual model here. This was our first LGR run, which can be closed or minimized. Here was the previous LGR chart analysis, which can be minimized. And now we're working on our other iteration or additional numerical realization from your conceptual model. So this corresponding numerical model can also be translated and run. When you do the translation, it'll create those files in a separate Modflow directory where you can also post-process if you need to, but you can also run this numerical model and get corresponding heads and results. And this allows you to compare different numerical model representations from one scenario to another. Essentially allows you to streamline the model development, so you don't have to worry about getting the right grid dimensions the first time. You can try several scenarios, whether they be 50-foot cells or 100-foot cells or whatnot, generate the numerical model and see what the results look like in a few mouse clicks, as you can see here. So that brings me to the end of the presentation. I'll open up the lines if there's any questions, then I'll take a look at any other questions that have come in through the chat. Let me take a look here. So again, thank you for your time. If there's anything you want to be clarified, certainly use this opportunity now to ask a question, and I'll do my best to answer it for you. A few few questions that came in through the chat. The first, when recently upgrading Visual MODFLOW, was indicated that VMODFLEX doesn't support transporter tests. When will these be supported? Answer, Jason, hopefully, is that we're working on having both those available by the end of the year. So we're currently starting the prototyping test. If there's any aspects of it that you wish to see, obviously outside of support for pilot points and SVD assist, etc., then certainly a welcome feedback, but we're hoping to have something available by the fall. For contaminant transport, we're currently focusing on MC3DMS, and that should be available by the end of the year. In the meantime, you can use VMODFLEX to design the flow model, assess different grid approaches. It generates standard MODFLOW files that you can import into Visual MODFLOW and then use the Visual MODFLOW classic environment for working with pest or contaminant transport. Another question, is it possible to use the inputs generated by Flex to run outside Visual MODFLOW? And yeah, I think I just answered that question for you. When you do the translation, as I showed you previously, it generates standard MODFLOW packages. So you can import those into Visual MODFLOW Classic using the import MODFLOW option if you need to work with some of the features that aren't in VMODFLEX yet. Hopefully that answers the question for you, Don.
Yeah, thank you.
Yep. Another question, are there tutorials for the MODFLOW Flex new version when you download it? I have the old version and got an email to get the new version. Yes, when you download it, there should be links that are available for building conceptual model, using several sample files, and importing existing Visual MODFLOW or MODFLOW files. So there's a couple different tutorials available along with corresponding supporting files. There's also documentation that helps to describe you how to create the child grids that I've shown you here and create inputs for Modflow LGR and run the model. I should mention that we'll make this webinar recording available on our blog posting in the next couple of days if you want to share it out with anyone else. Another question, which tutorial to start out with if one is using VMODFLEX for the first time? I think it depends on what your modeling approach is. If you have a set of numerical model files and you just want to see how they look and feel in VMODFLEX, then you want to follow the numerical model tutorial. If you're building a brand new flow model, you can follow the conceptual approach because then you can have all the benefits of assessing various grid approaches and whatnot. And the conceptual model is laid out in a very easy-to-use workflow approach as well. So ideally, the way we made the software is that you shouldn't have to refer to the documentation very much. The conceptual model workflow has these similar steps as well, where you just navigate through the steps using the forward and back buttons. Each step in the process, you have inputs that you need to provide in order for the conceptual model, and if you get stuck, then obviously you have the documentation as a backup. So if you're starting out with a new model, I suggest you go with the conceptual model approach. Is there any webinars planned in the future? Yes, we'll probably have a webinar again in the next 3 to 4 weeks highlighting some of the new things that we're currently working on, and these will be posted on our LinkedIn group and also on our blog posting. So if you're not currently available, I suggest you register on our blog site, on our website, or sign up for the LinkedIn group under Visual MODFLOW. Someone mentioned they missed the early part of the presentation. There will be a recording of this available, so we will make this like a recordable movie file that you can download in the next couple days. And as mentioned, there will be additional WebEx presentations in the coming weeks. If you want to learn more about the software, we're having online training in the second week of June, and if you're interested, you can sign up by contacting our sales department. And again, as an attendee for the webinar today, you're eligible for a 20% discount on that training. So I look forward, once you start using VMODFLEX, I look forward to any feedback or comments you have. LGR is certainly something new to what we've been working with in the past, 10, 15 years. So we hopefully have done it in a rather intuitive and logical approach. Handling several numerical models within a single environment can be challenging, especially when you have multiple child grids in one parent grid, etc. So any suggestions you have for improving that, I certainly welcome to hear those. Feel free to send them to our sales team, and they will be sent to me appropriately. Regarding future webinars, the best way to keep in the loop for those is to be signed up on our LinkedIn group. I believe we post all those webinar postings usually a few days or a week prior to the starting time, and you'll get notice for those through the LinkedIn group. Great. If anyone has additional questions or comments offline, just feel free to email our sales team and they'll redirect them to me. If not, I'd like to, again, thank you for your time, for attending the webinar today. I appreciate the time taken to learn about our exciting new software. And again, if you have any questions or comments, we're open to hearing those for you. So at this point, we'll end the session, and I wish you a good day.